This video is sponsored by Hungry Minds. Picture this, you're lying in a humming MRI machine and a nurse injects a dye into your arm. Moments later, the images on the screen light up, revealing vivid details inside your body. That dye isn't a dye at all, but a rare metallic element, gadolinium. Gadolinium is the secret ingredient that can make your inside glow on an MRI scan, at least on the scan images. It's a chemical element with some extraordinary talents and a fascinating story. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, hype, subscribe and hit the notification bell so you will never have to miss another episode. Also make sure to fill in the poll in the post section of the channel for next week, as we will be doing another deep dive into an element again. At first glance, gadolinium looks kind of awesome. The one in the cube looks dull, but if polished it looks like a silver coin or a small slab of chrome. It's silvery white, smooth and metallic, almost like it belongs in a sci-fi movie prop box. Now, if we could take it out of the cube and hold it with gloves, of course, we would notice it has a solid, slightly heavy feel. It's malleable enough to be shaped, but sturdy enough to feel like it means business. But here's the thing, it doesn't stay shiny for long. Once it's out in the open air, moisture and oxygen start reacting with it. The surface begins to darken, turning into a dull gray or black coating of gadolinium oxide. Now that layer doesn't protect the metal either. It flakes off, exposing fresh metal underneath, which also oxidizes. It's kind of like a croissant made of chemistry. Flaky, reactive, and not something you should be biting into. Which brings us to the question you creeps all want to know, can you lick it? Tempting as it may be, especially for the "I've licked a 9-volt battery before, how bad could it be" crowd, the answer is a firm no. Not sure who created the periodic licking table, but it seems pretty off here. While it's not radioactive or explosively reactive, gadolinium does become dangerous in contact with water, including the water in your mouth. That's because it can slowly release gadolinium 3+ ions, and those free ions are toxic. Inside your body, gadolinium can interfere with calcium signaling, damage kidney function, and potentially even mess with your nerves. It's so toxic in free form that medical use of gadolinium, like in MRI contrast agents, requires the metal to be safely trapped inside special chemical cages called chelates. These molecules lock the gadolinium ion in place so it can't wreak havoc. So while it might look like a high-end novelty chocolate bar, gadolinium is definitely not tongue-friendly. Best to leave this element to the scientists, the doctors, and the MRI machines. Or, in other words, admire the glow, don't taste the metal. The story of gadolinium begins in the 18th century with a mysterious black mineral found in a Swedish mine. In 1794, a Finnish chemist named Johan Gadolin analyzed the heavy black rock from the Utterby quarry in Sweden. He discovered it contained a new earth oxide, which we now know held a mix of rare elements. To honor Gadolin's work, that mineral was later named gadolinite. Fast forward to 1880, Swiss chemist Jean-Charles Galissard de Marignac was studying samples of gadolinite and another mineral called cerite. By examining the spectral lines, the unique light signature given off by these minerals, he spotted evidence of a new element. Marignac managed to separate a new oxide from cerite and initially called this mysterious element yttrium alpha, an alpha form of the element yttrium, which was found in gadolinite. A few years later, in 1886, French chemist Paul-Émile Lecoq de Bosbourdet independently obtained the oxide of the same new element. It was Lecoq de Bosbourdet who gave it the name gadolinium, in honor of Johann Gadolin, via the mineral gadolinite named for him. So gadolinium is one of the few elements named after a person, not directly, but through the person's namesake mineral. Ironically, the mineral gadolinite itself contains only a tiny trace of gadolinium, but it provided the clue needed to discover the element. Even after its discovery and naming, gadolinium remained hard to isolate in pure form. Throughout the late 1800s, chemists could only get gadolinium as part of mixed rare earth oxides. Separating one rare earth from another was a bit like trying to pick out an individual strand of cooked spaghetti. They're all very similar and tangled together. It wasn't until 1935 that pure metallic gadolinium was finally isolated by French chemist Félix Trombe. Trombe's achievement came long after gadolinium was recognized as an element, highlighting just how challenging rare earth elements were to separate. By the time gadolinium took its place in the periodic table, atomic number 64, symbol GD, scientists had begun to understand its remarkable behavior, especially its magnetism. But in the early days, gadolinium was mostly a scientific curiosity, with no major use yet. Its journey from lab curiosity to a vital material in medicine and technology would take most of the 20th century. So what is gadolinium like? In appearance, gadolinium is a silvery white metal, shiny and bright when freshly polished. It's moderately hard and quite malleable and ductile, meaning it can be bent or shaped without breaking. In fact, if you had a pure gadolinium metal sample, you could hammer it into a thin sheet or draw it into a wire. Properties it shares with many other metals. Its density is about 7.9 grams per cubic centimeter, which is pretty similar to that of iron. If you held a chunk of gadolinium in your hand, not recommended without gloves since it tarnishes easily, it would feel about as heavy as a same-sized piece of iron or steel. Now, like mentioned before, it reacts slowly with oxygen and moisture. Over time, it develops a dull, dark oxide layer on its surface, which we can see in the cube. Rather like how iron rusts, though gadolinium's oxide is black. In dry air, this tarnish takes a while to form, so a sample can stay silvery for a bit. But in humid air, gadolinium will lose its luster more quickly as the oxide film builds up. Fortunately, the oxide doesn't form a tight protective coat. It tends to flake off. When it flakes, a process called spalling, fresh metal is exposed, which then also oxidizes. So gadolinium can slowly crumble away if left unprotected. Kind of like a pastry that keeps on shedding flaky layers. Now, one of gadolinium's most outstanding physical properties is its magnetism. Gadolinium is like a magnet chameleon. Its magnetic behavior changes with temperature. At room temperature, around 20 degrees Celsius or 68 degrees Fahrenheit, gadolinium is strongly paramagnetic. This means it's not itself a magnet, but it's highly attractive to magnetic fields. In fact, gram for gram, gadolinium is one of the most paramagnetic elements known at room temperature. It really feels a magnetic field intensely. However, cool it down below about 20 degrees Celsius, slightly below room temperature, a temperature you might reach on a cool day or in a fridge, and gadolinium suddenly becomes ferromagnetic. Now, ferromagnetic is the kind of magnetism iron, nickel, and cobalt have. It can stick to magnets or even become a magnet itself. The temperature at which this change happens is called the Curie point, and for gadolinium, the Curie point is approximately 20 degrees Celsius. Just above that temperature, it won't stick to a magnet. Just below it, it will. Imagine a metal that's non-magnetic in your warm hand, but turns into magnetic material if you cool it in an ice bath. That's gadolinium. Gadolinium also shows the magnetocaloric effect, which is a big phrase that means it can heat up when placed in a strong magnetic field and cool down when it's removed from that field. If you take gadolinium metal and put it between the poles of a powerful magnet, its temperature will rise a little as it becomes magnetized. Take it out of the magnetic field and it cools back down. This heating and cooling cycle might seem odd, but scientists have figured out how to use it to design magnetic refrigerator devices that cool things using magnets and special elements instead of the traditional gas compression. Gadolinium's magnetocaloric effect is strongest near its Curie point, around room temperature, making it a superstar candidate for these new refrigeration technologies. In terms of other physical stats, gadolinium melts at a high temperature, about 1313 degrees Celsius or 2395 degrees Fahrenheit, and boils at an extremely high temperature, over 3000 degrees Celsius. These numbers tell us that it takes a lot of heat to get gadolinium to change states, which is typical for metals that have strongly bonded atoms. Now, it's also a hexagonal crystal at room temperature. Imagine its atoms packed in a hexagonal pattern. And if you heat it above 1235 degrees Celsius, it shifts into a different atomic arrangement, body-centered cubic structure. But those details are more for the materials scientists. The main takeaway is that gadolinium is a durable metal with a high melting point and boiling points. Another fascinating fact, among all stable elements, gadolinium has one isotope, a specific type of atom, that is an incredible absorber of neutrons. The isotope gadolinium-157 holds the record for the highest known neutron capture ability of any stable element, except one radioactive competitor, xenon-135. In plain terms, gadolinium-157 is like a sponge for neutrons. This property makes gadolinium very useful in nuclear applications, as we will see later. Chemically, gadolinium behaves much like its rare earth neighbors in the periodic table. It's a reactive metal, though not as extremely reactive as alkali metals like sodium. Gadolinium's most common oxidation state, the charge it tends to have in compounds, is +3. This means that when gadolinium forms compounds, it typically gives up 3 electrons and forms triply charged ions, gadolinium +3 ions. Those gadolinium ions are colorless in solution and often exist surrounded by water molecules or other ligands, molecules attached to the metal ion. Just like most lanthanides are the family of rare earth elements from lanthanum through lutetium. Gadolinium-3 compounds are usually what you get, whether it's gadolinium oxide, gadolinium chloride, gadolinium nitrate, and so on and so forth. One convenient thing about gadolinium metal is that it's a bit more stable in air than some of its immediate neighbors like europium. If you have metallic europium, it will oxidize and tarnish almost instantly in air. Gadolinium, by contrast, can hold out a little bit longer, especially in dry air. But as mentioned earlier, in moist air it will tarnish, forming gadolinium-3 oxide. The chemical reaction can be summarized as this. Like also earlier mentioned, this oxide doesn't stick well to the metal surface and flakes off, so the oxidation can keep going. Gadolinium is also quite electropositive, meaning it readily gives up electrons to form positive ions. As a result, it reacts slowly with cold water and more rapidly with hot water. When gadolinium metal reacts with water, it produces gadolinium hydroxide and hydrogen gas. So gadolinium will rust in water in a way, forming an hydroxide and releasing hydrogen. It's not as vigorous as, say, sodium reaction with water, which is explosive, but it is an active metal nonetheless. Now, when it comes to acids, gadolinium dissolves in most dilute acids, like hydrochloric or sulfuric acid, to form solutions containing gadolinium-3+ ions. For example, in dilute sulfuric acid, gadolinium will form gadolinium sulfate, a salt, while releasing hydrogen gas. Interestingly, one acid gadolinium doesn't react with is hydrofluoric acid. And that is because hydrofluoric acid forms a protective layer of gadolinium fluoride on the metal that stops the reaction. Another chemical quirk, gadolinium is a strong reducing agent, especially at high temperatures. This means gadolinium metal can reduce or strip oxygen from oxides of other metals. For instance, if you have an oxide of iron or chromium, mixing it with gadolinium metal at high heat might result into gadolinium oxide forming and the iron or chromium being freed as pure metal. This property is quite useful in materials chemistry. Gadolinium can also form compounds with many nonmetals. For example, if you heat gadolinium with sulfur, you get gadolinium sulfide. With nitrogen, gadolinium nitride. With carbon, gadolinium carbide, and so on and so forth. These binary compounds, one part gadolinium, one part another element, often require high temperatures to form, and they typically feature gadolinium in that +3 state, combined with the other element. One aspect of gadolinium's chemistry has a huge practical importance. Its compounds can be fluorescent or phosphorescent. Many gadolinium-3 salts, when doped with certain other elements, will glow under specific conditions. For example, gadolinium compounds activated with terbium are used as green phosphorus in old-style color TV tubes and X-ray imaging screens. But we're getting ahead of ourselves. We will cover those uses soon. Now, before moving on, it's important to mention what gadolinium is not. Despite being a metal, you won't find gadolinium coins or jewelry or structures. It's too reactive and too scarce for such uses. And unlike some other well-known metals, gadolinium has no known biological role in our bodies. You don't need gadolinium in your diet, and in fact, free gadolinium ions are toxic to living organisms, as mentioned earlier. Its value comes not from everyday presence, but from very specialized roles that depend on its unique physical and chemical traits. If gadolinium is so useful, you might wonder, where do we get it from? Well, gadolinium is not found in nature as a free metal, because it reacts with oxygen, water, and other elements. Any gadolinium that was in the Earth's crust long ago is now locked away in minerals, chemical compounds in rocks. It is also a rare earth element, and like its rare earth cousins, gadolinium is scattered in various minerals, usually alongside other lanthanides. Two of the most important gadolinium-bearing minerals are monazite and bastanaazite, and we've discussed them many times before. Monazite is a reddish-brown phosphate mineral that contains a mix of rare earth elements, mostly cerium, lanthanum, neodymium, etc., and a bit of gadolinium in the mix. It often occurs in beach sands and alluvial deposits in places like India, Brazil, or parts of Africa. People have mined monazite sands to extract rare earths. Bastanaazite is a different kind of mineral, a rare earth fluorocarbonate that has been mined notably in places like Mountain Pass, California, and in China. Bastanaazite ores are a major source of lighter, rare earth elements and contain some gadolinium as well. Interestingly, gadolinium got its name from gadolinite, as we discussed, but gadolinite itself isn't a major commercial source of gadolinium. Gadolinite is relatively scarce and contains a variety of rare earths, yttrium, cerium, etc., with only a small fraction of gadolinium. In the Earth's crust, gadolinium is more common than its rare label might suggest. It's estimated to be about 6 to 7 parts per million in abundance in the Earth's crust. That might sound tiny, but compare it to the truly rare element like gold, around 0.004 parts per million. Gadolinium is 1,000 of times more abundant than gold. In fact, gadolinium is about as abundant as tin or cobalt in the crust. However, finding it in high concentration is the tricky part. Rare earth elements tend not to form big, rich ore veins like gold or copper do. Instead, they are found dispersed together in those special minerals. So gadolinium is rare in the sense that it's rare to find it isolated. But in total amount, there's quite a lot to go around. The world's major rare earth deposits contain gadolinium along with all the other lanthanides. One of the biggest sources is the Bayan Obo deposit in Inner Mongolia, China. That deposit is mined primarily for iron, but it also yields a huge amount of rare earth elements as byproducts, including gadolinium. Over the past few decades, China has become the dominant supplier of rare earth, including gadolinium, to the world. Other countries' significant rare earth production include the United States, for example, with Mountain Pass Mine, Australia, Mount Weld deposit, and some in Asia, Africa, and the Americas. Even some sands in Sri Lanka, India, are a source of gadolinium via monazite. Global reserves of gadolinium, in the form of rare earth ore that could be mined, are estimated to be well over a million tons. That means that if we needed more gadolinium, geologically speaking, there's a lot out there. But not all of that is economically or easily accessible. As of recent years, the world produces only a relatively small amount of gadolinium per year. Exact figures vary, but on the order of a few hundred to a couple of thousand tons of gadolinium in pure form or high concentrate are extracted annually. This is enough to meet the demand since gadolinium's uses, while crucial, are mostly niche and high-tech. How do we go from gadolinium buried in rocks to a shiny metal or useful compound? The production of gadolinium is a complex multi-step process, mainly because gadolinium is never alone. It always mixed with other rare earth minerals. Let's walk through a simplified version of the typical extraction process using monazite or bastanaazite ore as the starting point. The rare earth ore, like monazite or bastanaazite rock, is crushed into a fine powder. This powder is then digested with strong acid, often sulfuric or hydrochloric acid. The acid breaks down the mineral structure, converting rare earth compounds into soluble forms. For example, if using hydrochloric acids, rare earth phosphates in monazite might be converted into rare earth chlorides in solution. Rare earth ores often contain other elements like thorium, which is radioactive, or iron. The acidic solution is partially neutralized, raising the pH to precipitate out things like thorium as an insoluble hydroxide. Next, the rare earth elements themselves are precipitated out. A common method is to add ammonium oxalate, which reacts with rare earth ions to form insoluble rare earth oxalate salts. These oxalates drop out of the solution as a solid. The collected rare earth oxalate solids are then heated calcined strongly, which decomposes them into oxides. For instance, gadolinium oxalate becomes gadolinium oxide upon heating, releasing gases like carbon dioxide in the process. Now we have a mix of rare earth oxides, including gadolinium oxide, but also others like cerium oxide, neodymium oxide, etc. One trick often used to dissolve this mix in an acid that will leave one major component behind. For example, gadolinium oxide and most rare earth oxides will dissolve in nitric acid, but cerium oxide will not. If cerium oxide is in the cerium 4+ state, this step can remove cerium, a large fraction of the mix, by leaving it as an insoluble residue, while the rest, including gadolinium, go into solution. Now, the solution still contains a soup of rare earths that are chemically very similar. To separate gadolinium from its cousins like europium and samarium, which often accompany it closely, advanced techniques are used. Historically, chemists performed endless fractional crystallization, repeatedly crystallizing and dissolving salts to slowly tease apart elements, an incredible time-consuming task. Today, ion exchange chromatography and solvent extraction techniques are the go-to methods. In ion exchange, the mixed rare earth solution is passed through special resin columns that bind ions differently. By washing the column with just the right substances, specific elements come out at different times. Through a series of such steps, gadolinium can be isolated in fairly pure form. At this stage, we might have gadolinium in the form of a compound like gadolinium oxide or perhaps gadolinium chloride. To get metallic gadolinium, a reduction step is needed. One common method is metallothermic reduction, where a more reactive metal like calcium or lithium is used to yank the oxygen or chlorine away from the gadolinium. For example, gadolinium oxide can be mixed with calcium and heated in a vacuum or inert atmosphere. Calcium will oxidize, turning into calcium oxide, and gadolinium will be freed as a metal. Another method is electrolysis of molten salts containing gadolinium. But since gadolinium has a high melting point, direct electrolysis is challenging, so the metallothermic route is more frequently used. The result of these steps is usually a sponge of gadolinium metal, a porous mass of metal, which can then be melted and cast into ingots or processed further if very high purity is needed. This whole production process is quite involved, and it's typically done in facilities that handle a range of rare earths, not just gadolinium alone. Often, gadolinium is recovered as part of the collective process of rare earth ores and then further refined. The difficulty of separating rare earths is one reason they were considered a mere curiosity in the 19th century. It was just so hard to get a pure sample. Modern chemistry and industrial processes have thankfully made it easier, though still not trivial. Now that we have our gadolinium, either as a metal or in useful compound forms, what do we do with it? Let's explore the many applications of this glow-making element. Perhaps the most famous role of gadolinium, and the one hinted at in the title of this piece, is medical imaging. Specifically, gadolinium is widely used as a contrast agent in MRI scans, magnetic resonance imaging. If you've ever had an MRI with contrast, the contrast agent was very likely a gadolinium-based compound. Now, why use gadolinium in MRI? MRI machines create detailed images of the insides of our bodies using powerful magnetic fields and radio waves. They map where hydrogen atoms, mostly in water molecules, are in our tissues. Normally, all your water is about the same, so images can be a little blend. But gadolinium has a trick. It's paramagnetic, meaning it influences magnetic fields in its vicinity. When a gadolinium-based contrast agent is injected into a patient, it circulates through the bloodstream and into tissues. The gadolinium doesn't glow in a visible sense, but it alters the local magnetic environment in a way that the MRI scanner can detect it. Essentially, gadolinium shortens the relaxation time of nearby hydrogen nuclei in water. In plain English, this means it makes certain areas appear brighter or higher contrast on the MRI images. Tumors, blood vessels, inflamed areas, these often light up when gadolinium contrast is present, because the gadolinium concentrates there, either by leaking out of blood vessels in abnormal tissues, or just by being in the blood vessels itself. We call these substances gadolinium-based contrast agents, GBCAs. They are usually gadolinium ions chelated, bound, by large organic molecules. The chelator molecules wrap around the gadolinium-3+ ions like a claw, which is crucial for safety. Remember how free gadolinium ion is toxic? The chelation keeps it bound so it doesn't interact with the body's tissues or cause unwanted chemical reactions. The most common contrast agent for many years was gadopentate dimeglumine, brand name Magnevist, among others. There are also agents like gadodiamide and gadobutrol, I really hate this segment, and so on. Each is a different chelated gadolinium compound. When you get an MRI contrast injection, within seconds the gadolinium agent is highlighting your blood vessels and organs. Radiologists can clearly see things like tumors, which often have leaky blood vessels that let gadolinium through, making them shine on the scan, or detect multiple sclerosis lesions in the brain, or visualize the structure of the heart and arteries. Gadolinium contrast has been a game changer for diagnostic medicine. Since the late 1980s, when the first agents were approved, hundreds of millions of doses have been given worldwide. It's so common that many people have gadolinium in their bodies for a short time during some point in their lives, thanks to the MRI scan. Let's address the safety aspect with a simple explanation. Free gadolinium in the body would be very bad. It could interfere with biological processes since gadolinium-3+ can block calcium channels and do other nasty things. But in chelated form, gadolinium is much safer because the gadolinium ion is caged. In people with a normal kidney function, about 90% or more of the injected gadolinium agent is excreted in urine within 24 hours. It doesn't typically accumulate. However, if someone has severe kidney problems, their body might not clear the gadolinium quickly, and in rare cases, this has led to a condition called nephrogenic systems fibrosis, NSF. NSF is a serious complication where skin and other tissues become thick and hard. Because of that risk, doctors avoid giving gadolinium contrast to patients with a poor renal function, or use certain newer agents that are considered safer in that context. Additionally, trace amounts of gadolinium have been found to linger in the body, like in the brain, after repeated scans even in healthy people. And researchers are studying what that means. So far, no clear harm has been shown from these traces. But it's an area of active research, and some newer contrast agents aim to use lower doses or different formulations. Now, as mentioned earlier, gadolinium has a sort of superpower when it comes to absorbing neutrons, especially one of its isotopes, gadolinium-157. This makes it extremely useful in nuclear reactors and related technology. One key use is as a neutron absorber in nuclear reactors. In reactors, controlling the rate of the fission chain reaction is critical. Materials that absorb neutrons can be used to regulate the reaction. For example, control rods that you insert or remove from the reactor core to absorb neutrons and slow down the fission. Gadolinium, often in the form of gadolinium oxide, is sometimes used in control rods or as a coating on them because it's so effective at gobbling up neutrons. Gadolinium is also used as a burnable poison in nuclear fuel. That phrasing sounds odd. Why would you put poison in fuel? In reactor design, a burnable poison is a material that at first absorbs a lot of neutrons, thus poisoning the reaction, but gradually burns away, transform as the reactor operates. Fresh nuclear fuel is very reactive, lots of excess neutrons, which could make a new reaction core run too hot initially. By mixing in a bit of gadolinium, maybe gadolinium oxide mixed into the fuel pellets, the reactivity is tamed at the start. The gadolinium soaks up neutrons over time as the uranium fuel is used up and naturally becomes less reactive. The gadolinium is also getting used up, transmuting into other isotopes that aren't as absorbent. So the effect is that the reactor's performance evens out over the fuel's life. Gadolinium is excellent for this because of that huge neutron capture cross-section, and it conveniently takes itself out of the game by transmuting as it absorbs neutrons, turning into isotopes of terbium, samarium eventually. Many modern nuclear reactions, especially some types of pressurized water reactors and the CANDU heavy water reactors, utilize gadolinium as a burnable poison. Another nuclear-related use of gadolinium is in nuclear radiography and detectors. In some neutron radiography, imaging techniques using neutrons instead of X-rays, gadolinium sheets can be used to capture neutrons and emit gamma rays or electrons, which then form an image. In radiation monitoring, gadolinium's neutron absorption can help detect the presence of neutrons, indicating radioactive sources, etc. Now here is a very cool and exotic application, neutrino detection. In massive physics experiments like the Super Kamiokande Neutrino Observatory in Japan, scientists are looking for elusive neutrinos, tiny subatomic particles. When a neutrino interacts with the detector, which is essentially a huge tank of very pure water, it can produce a small flash of light or a chain of reactions. By dissolving a gadolinium compound in the water in a very small amount, the detector's sensitivity is enhanced. Here's how it works. A neutrino interaction can produce a free neutron. Gadolinium readily captures that neutron and then emits a cascade of gamma rays. Those gamma rays produce the telltale flash of a light that the detectors pick up. In essence, gadolinium acts like a magnifying glass for the signal, making it easier to spot when a neutrino has interacted. The addition of the gadolinium to the Super K detector was a big development, playfully named the gadolinium upgrade by physicists. Gadolinium is also used in combination with other rare earth to make specialized garnet materials. Garnet aren't just pretty gemstones in the tech world. A garnet is a type of crystal structure. Gadolinium gallium garnet, GGG, is a synthetic crystal that was used in certain optical applications and as a substrate for magnetic bubble memory in early computing. Bubble memory was an old form of data storage in the 1970s that used magnetic domains in materials like GGG. An interesting historical footnote. In fact, gadolinium gallium garnet can form clear sparkly crystals and was once used as an affordable imitation of diamonds and jewelry, before other similants like cubic zirconia took the spotlights. Gadolinium yttrium garnet, often with other additives, is used in some microwave and optical components as well. These garnets can manipulate light or microwave signals, useful in telecommunications and radar systems. Another realm where gadolinium shines, literally, is phosphors and scintillators. Phosphors are materials that emit light when energized by X-rays, electrons, etc. And scintillators are materials that light up when hit by high-energy particles or radiation. Gadolinium compounds are key in many of these. For example, gadolinium oxysulfide, when doped with terbium, is a very efficient green phosphor. It has been used in the screens of X-ray detectors and medical imaging systems. When X-rays hit the screen, the gadolinium-based phosphor emits green light, which then either exposes film or is read by a digital sensor. This helps convert X-ray images to visible light images, greatly enhancing the efficiency of X-ray imaging. So let's talk about that magnetic refrigeration again, but from a practical tech perspective. Gadolinium metal itself can serve as the core of a magnetic cooling system, and indeed, in 1976, engineers at NASA built experimental magnetic refrigerators using gadolinium. They cycled gadolinium in and out of strong magnetic field and used a fluid to carry heat away, creating a cooling effect. It was a proof of concept that magnetic refrigeration could work near room temperature. Modern research has found alloys of gadolinium, like this one, that have an even larger magnetocaloric effect and can be turned into different temperature ranges by adjusting the mix of elements. The goal is to create refrigerators and air conditioners that don't use greenhouse gas, refrigerators, or noisy compressors. Instead, they use magnetization cycles. It's a promising technology for the future of efficient cooling, and gadolinium played a starring role in getting it off the ground. One could joke that gadolinium can literally keep it cool under pressure by leveraging its magnetic heat dance. Now, every time we talk about chemistry, we really think about the building blocks of civilization. The elements, the reactions, the stuff that literally makes up everything around us. And that actually reminds me of a Kickstarter I backed a few years ago. Now, what we have here is the ultimate guide to rebuilding civilization, created by Hungry Minds, an international collective of artists, scientists, designers, and architects who build cultural projects that celebrate human curiosity. And this book, honestly, is one of the most fascinating objects I've added to my workplace. It's 400 plus pages of inventions, discoveries, and ideas that shaped humanity, all illustrated in this really unique blend of engineering, drawings, medieval art. The print quality is gorgeous, premium matte art paper, a solid laminated hardcover, and illustrations that feel both scientific and mythic. It's the kind of book you keep on your desk because it inspires you just by being there. Now, what surprised me most about this book is how universal it is. Whether you are into physics, philosophy, engineering, or art, there is something inside you that trips a mental switch and makes you think bigger. And since we just moved from chemistry into materials, check this out. Now, if you're looking for a Christmas gift that is more meaningful than the usual stuff, something beautiful, intellectual, rich, and honestly a joy to flip through, this is it. It became a global success on a Kickstarter and an Indiegogo, raised over $2.3 million, and it was a bestseller last year for a reason. I've put a link in the description along with a special Christmas discount so you can grab your copy. It's a gift that lasts, sparks conversations, and fits perfectly into a cozy holiday setup. Lights, candles, a warm drink, all the things that make December feel magical. Use the QR code, click on the link in the description, and use the promo code CubeChemistry10 to get your 10% discount. So if you want to surprise someone curious or yourself, definitely check out the book by Hungry Minds. This unassuming rare earth metal, named in tribute to a pioneering chemist, stayed in the shadows for nearly a century after its discovery. Yet today it quietly serves us in hospitals, labs, and industries worldwide. Next time you see the bright highlighted details on an MRI image, remember that it's gadolinium doing the work behind the scenes. A metallic magician making things visible. When you hear about advanced nuclear reactors being safely controlled, or new refrigeration technologies that could save energy, or high-performance materials in electronics, chances are that gadolinium has played a part there too. Now, we would like to members that support our channel. Thanks for doing this. We really appreciate you. Now, if you think we missed anything, tell us in the comments. And if you want to know more about another lanthanide that is powering our world, watch this episode about samarium next.